Welcome back. We are wrapping up the course with a discussion of the future of SDN. This module has two lessons. In the first, we will talk about a broader vision for SDN beyond the OpenFlow protocol and match action rules. The current SDN paradigm is based on switches that perform one or more actions based on match conditions for fields in packet headers. Both the current set of fields and conditions that a switch might match on and the set of actions are limited. For example, the OpenFlow protocol does not allow match rules based on properties of a packet payload, nor does it provide for switches to perform more complicated actions, such as transcoding, encryption, or deep packet inspection. Keeping in mind that software-defined networking entails far more than just the provisions of the current OpenFlow protocol, one can think about how to expand both the set of conditions or properties that a switch might match traffic on and the set of actions that a switch might take upon a successful match. Expanding software-defined networking beyond match action requires a practical approach. One option might be to expand the current OpenFlow standards. Of course, this requires some amount of consensus as well as support from vendors. Another option is to implement a much richer data plane at the controller, so that any complicated match action primitives might be implemented at the controller itself. This offers considerable flexibility, but also incurs severe performance penalties. A third option is to send traffic through custom devices like middle boxes or custom packet processing hardware. This is the approach that we'll explore in this lesson. Of course, this approach makes sense, but it also requires the SDN controller to orchestrate the process of redirecting traffic through the appropriate set of middle boxes that can perform these more sophisticated actions. In the rest of the lesson, we will look at two future directions. One is the use of an SDN control plane to orchestrate network middle boxes, and the second is the use of an SDN control plane to direct packets through custom programmable hardware. There is initial work on both of these directions, but it is safe to say that both of these directions are fairly nascent and early stage. Let's now take a look at an SDN controller that performs middle box orchestration, called SLIC. In contrast to a conventional SDN controller that simply installs flow table entries and switches, the SLIC controller performs an additional set of functions. First, it installs element code and configuration on middle boxes throughout the network. Second, if these software elements running on middle boxes raise triggers or exceptions, the SLIC controller is equipped to handle those exceptions. Finally, the controller installs flow table rules into the switches in the network to redirect the appropriate traffic flows through the middle boxes to ensure that the appropriate subsets of traffic are processed by the code that the controller installs in the middle box elements. SLIC elements can be arbitrary code that conform to a standard API. They can also raise triggers at the controller, at which point the controller might perform a more sophisticated set of actions. Each element has a self-describing manifest that lists the hardware requirements for running that element, the list of triggers that it might expose, and the requirements for running that element. For example, the need to see traffic flows in both directions, or all traffic from a host. Listing the hardware requirements in a manifest ensures that the software element is only placed on a middle box that is capable of running the element. A SLIC application that runs on top of the controller implements network policies. It dictates which elements should be run on which subsets of traffic and what action should be taken in response to changes in network conditions. The SLIC controller abstracts many details away from the application, so the application does not need to specify where the elements should be placed in the network or how traffic should be steered or routed towards those elements. Those problems are handled behind the scenes by the SLIC controller. The controller manages and configures the network of middle boxes. It implements resource discovery, in other words, figuring out which middle boxes are capable of running which elements. It deploys and removes these elements on the various middle boxes in the network, and ensures that middle box functions continue to be performed even in the face of failure. The controller also implements policies for the application. For example, figuring out where on the network to place an element and how to steer traffic towards those elements. One possible application of SLIC is the dynamic redirection of certain subsets of traffic to deep packet inspection devices upon the discovery of suspicious behavior. For example, a lightweight middle box process might inspect all DNS traffic and look for DNS lookups to domains on a blacklist. If such a suspicious DNS lookup takes place, the controller might want to redirect all of the corresponding flows through a deep packet inspection device or a traffic scrubber. A second approach for broadening the vision of SDN is to expand the match action paradigm by installing custom packet processing hardware in the network and using the SDN control framework to orchestrate traffic flows through those custom packet processors. At Georgia Tech, we are augmenting OpenFlow switches with custom packet processors and designing a device abstraction layer that allows the programmability of this substrate, both for a single device and across an entire network. The idea behind the architecture is to use OpenFlow rules to redirect certain subsets of traffic to custom packet processors that sit beside the OpenFlow switch. In other words, in addition to using flow table entries simply to choose an output port for a traffic flow, the flow table entries might redirect subsets of traffic through custom packet processors before they are ultimately passed to the output ports. There are many possible applications for this type of custom data plane orchestration, involving big data, on-the-fly encryption, transcoding, or traffic classification, and deep packet inspection for subsets of traffic, including the application we just looked at in the middle box scenario. In summary, there are many new frontiers for SDN, more than we can cover in just a single lesson. But one of the most exciting frontiers for SDN is to recognize that SDN is in fact much broader than the OpenFlow protocols and match action primitives. SDN is about separating control and data plane, and using the control plane to perform orchestration that might otherwise be extremely difficult. In this lesson, we've looked at two examples of how SDN controllers might be used to orchestrate middle box functionality and redirection of traffic through a programmable hardware substrate. In the next lesson, we will look at a wider range of open problems that SDN faces.